Hello to you. My name is Stefan Hollands. I'm a professor in theoretical physics at the University of Leipzig and a scientific member of the Max Planck Institute here in Leipzig. Today, I would like to understand a little bit what I'm doing scientifically, what are my interests, what I would like to do in the future. Broadly speaking, my interests are in the areas of classical general relativity, GR, and quantum field theory. Classical general relativity was introduced by Einstein about 100 years ago. Its purpose is to give a theoretical description of space-time at a very large-scale structure and to describe massive objects such as the Earth, the Sun, or even things like black holes. Quantum field theory is a theory that has been invented about 70 years ago, or maybe 100 years ago also, if one is generous, and its purpose is to describe elementary particles. So it's the opposite. It's to understand nature at its very smallest scales. Within these subjects, which are enormous in themselves, I'm interested in specific subtopics which have an overlap with each other. So in general relativity, I've been interested in classifying solutions of this theory which describe black holes. This is an interesting subject because black holes are real, but it's also an interesting mathematical subject because solutions tend to be much more unique than you think. So think of as the sun, which is described by many parameters. A black hole typically is described by very few parameters. So there's a chance that you can say what all possible black holes are mathematically in this theory of Einstein. I've also been interested in questions related to the stability of these objects, whether the slightest perturbation will make them explode or implode, or whether the slightest perturbation will just decay and the object will basically remain what it is. A related issue is what is the structure of the gravitational field very far away from the object? This is the topic of asymptotic symmetries in general relativity. And very much of interest today from an experimental viewpoint is the two-body problem, which concerns the question what happens if two bodies, such as two black holes, orbit around each other, gradually approach, and eventually merge. What can we see as an observer on Earth of this very violent event? In quantum field theory, I'm interested in questions of so-called renormalization group flow, which is the question how the theory looks on large and very small scales. So how does the theory apparently change if we zoom in onto the tiniest length scales? Related to general relativity is the question how quantum fields, how elementary particles behave on a curved spacetime, a spacetime that's shaped by a gravitational background field. And very much a topic of great interest recently, with the advent of the discovery of Hawking of entropy of black holes and Bekenstein, is the relation between quantum field theory, quantum information theory, the theory how to transmit quantum information, and general relativity. Now, concerning the question of black hole stability, I've made with Robert Wald and also related to other people's work, important progress, I think, how you can understand instabilities of black holes by their analogy to thermodynamics. So in thermodynamics, if you have an object with an unusual sign of the heat capacity, it will become favorable for this object to distribute the energy density in an inhomogeneous manner. So black holes have many properties that are reminiscent of black bodies. So it's a very natural question whether similar considerations apply to black holes. And in fact, they do, as originally pointed out or conjectured by Gupse and Mitra. What we did was to relate these ideas to the powerful machinery of partial differential equation, allowing us to prove things like if you have a black hole that's rotating very fast, such as depicted by this oblate disk there, describing sort of the surface of the black hole, then it can become entropically favorable, so you can increase the entropy of this black hole by putting on small ripples onto it, and thereby the thermodynamic picture tells you that this object should be unstable. So our theory is able to give proofs of such intuitive ideas, and therefore it's a new window into the question of stability of black holes, which otherwise is a very, very complicated question. So it gives a new conceptual view on this kind of instability phenomenon, which in my area, theoretical physics, is always a very welcome thing, because you get a kind of a qualitative picture of things. You're not so tied to solving complicated equations, but you get an understanding of why things work in one way or another. Asymptotic symmetries are about the space-time structure very, very far from a massive object. So typically one has in mind a massive object as depicted in this cartoon, perhaps consisting of two massive bodies that in spiral perhaps merge and emit gravitational radiation. So while the gravitational field that's stirred up by this merger is very complicated in the inside, the signature of the merger, so the gravitational ripples of space-time propagating outward to infinity, have a certain more universal character, and one can think about characterizing them, for example, through the displacement of inertially moving observers. So this is a topic that relates scattering theory of graviton to black holes, even to questions about information theory related to black holes. What the space-time remembers about the collapse of the black hole at very far distances. I've already mentioned quantum information theory a few times. So what is quantum information theory? Quantum information theory per se has nothing to do with gravity or with quantum field theory. It's just a bunch of ideas that are aimed at thinking about how information can be transmitted or manipulated if your system isn't classical, like a usual computer, obeying to a very good approximation the laws of classical physics. But if you have a device that's generally built out of, that generally obeys the laws of quantum theory, not classical physics. So this is a huge subject in itself, but because its ideas are so general, they can be applied to basically any quantum system, and in particular the ideas can be applied to quantum field theory. In quantum field theory, one thinks of information or excitation or quantized excitation of some fields, such as the electric or the magnetic field, as localized in certain regions, as depicted there. And then one question is how, if you have a state, information in one region is correlated, or we say entangled, with information in the other region. So you can think of this as the basis for a real process such as teleportation or encryption, but you can also think about it in a more fundamental way. And what we have done is to analyze noisy channels in the context of quantum field theory. How much information can you get back if you pass a string, a piece of quantum encoded information through a noisy channel where you know you're going to lose some information, but how much can you get it back? This is a very relevant question in context also involving the gravitational field. And here I've given you some references to some of our work. The two-body problem in general relativity, by contrast, is not related to quantum ideas of quantum theory, but is really the problem of calculating what observational signatures you can get if you have somewhere in your space-time a, say, very large or very massive object, such as a black hole here, which is orbited around by a smaller, or perhaps much smaller, test object. So now the test object doesn't have to be much smaller, but this kind of setup is relevant for future observations of gravitational waves, because once an object rotates around a massive object, it creates ripples in space-time in the form of gravitational waves. These gravitational waves get emitted. We can ideally receive them. We can learn something about the orbit of the object by analyzing the gravitational wave. And we can understand how this object, while emitting gravitational wave, will lose its energy and eventually plunge into the big one. The plunge is a very violent process, and we can expect to get signatures about that plunge. But to understand that signature, we really must understand how this is gradually plunging into it over time. So the orbit will get closer and closer to the black hole over a relatively long time. So this is a mathematically complicated problem, because the gravitational waves propagate in the space-time created by the larger black hole, and also the gravitational waves themselves modify the space-time, creating a force onto the object, so-called self-force, because it's created by the self-field of the object. And therefore, this creates a lot of difficult technical problems, and calculating these orbits and waveforms is one of the major tasks if one wants to get predictions for future gravitational wave detectors, attempting to measure such kinds of inspirals. Now, another subject also relates to black holes, but this time also to quantum theory, is the question, what happens inside a black hole? Now, if you're probably not familiar, if you see this, with how you describe black holes in general relativity, but one way that doesn't require too many formulas is to draw such kind of diagrams here, which were invented by Penrose and are called Penrose diagrams. In a Penrose diagram, the gravitation of the space-time is reduced to a two-dimensional thing by suppressing all angles, so you don't see any solid angle you're pointing at, and also you apply a certain stretching to it in such a way that you can get the entire space-time, which is infinitely extended, on a sheet of paper or on a slide like this. And if you have done this, once you have done this, you can read off from this sheet, from this drawing, from this picture, this Penrose diagram, how light can propagate. And the simple rule is that light can propagate at 45 degrees like this, or having suppressed the angle, it can propagate like this inside this so-called light cone. So the brilliant thing is you can read off, given such a diagram, what kind of regions you can reach by emitting a signal from some other region. So, for example, the region 1 here represents everything that's outside of the black hole. So you see that a point here can emit light only within this sector of at most 45 degrees, so it cannot propagate outside. That's why it's called a black hole. Once you're inside, you can't tell your outside friends how you're doing. Now, this black hole has not just this inside region, but it has a certain region beyond that, which is separated by this other line of 45 degrees, and which is called a horizon. This inner horizon is something that you are going to cross if you are going to decide to fall into the black hole. So this line here is a horizon that separates the inside from the outside. This horizon here is some other thing that separates the singularity, where space-time becomes, where the gravitational field becomes so violent that you're going to be crushed or stretched, or at any rate you die, from the region where the inside of the black hole where you don't die. So a natural question is what actually happens, what an observer actually sees if he were to dive into it. So in quantum information theory and physics, if you have two observers, they're always called Alice and Bob. And this time Bob is diving into the black hole as given by this, as shown by this blue line, which is the world line of Bob, which is the curve he traces out over time. So he starts from the outside, he moves inside. And once he crosses this horizon, there's something strange, because what's happening once he crosses this inner horizon cannot be predicted from knowing everything that was all the values of all fields in the past. So this issue of indeterminism is sometimes called, there's a resolution to this, sometimes called the cosmic censorship conjecture. And the cosmic censorship conjecture says that somehow effects of field propagation along these horizons pile up in such a way that you kind of die, you see an infinite gravitational field even before you are going to enter this region where you have problems with determinism. There's a mathematical formulation of this given here. So this is a question that you can prove, or this is an issue that you can address using techniques from partial differential equations propagating on this kind of black hole space-time, and this is what people have very much done. However, an interesting fact is that you can have quantum effects too, and you can ask whether quantum effects are even stronger or weaker. So normally in everyday life, a quantum effect is associated typically with a microscopic system of very low energy, whereas here it's associated with a macroscopic object. So this is a question that in my group we've been addressing and looking at. Also, this is a question that many people have been looked at, but we have been applying our knowledge of quantum field theory to give rigorous and strong answers to this kind of questions. So in the classical case, the pile up of the gravitational field, or the increase of the gravitational field, can be illustrated by thinking about two observers. Now Alice comes into play, where Alice stays outside, being more cautious than Bob, but sends him periodic signals. These periodic signals, because of some version of the time delay effect in general relativity, will pile up for him, even though she sends them at equidistant time interval according to her clock. They will pile up for Bob. And this pile up of signals corresponds to a pile up of waves, which makes him think that this horizon is really a singularity. In quantum theory, it turns out that quantum fluctuations create an even stronger singularity. And this even stronger singularity persists even in cases where classically the blow up of the perturbations is so weak that you could in fact think of entering this forbidden, as I call it, forbidden region. It's not forbidden classically if the pileup is weak, but it's a region where somehow the singularity starts to shine at you, and you don't know what's coming out of the singularity, and therefore you have an issue with determinism. So finally, let me point out some math that's related to my research. This has been very qualitative, but there's a lot of math behind it, as there is generally in theoretical physics. For me, there's even more, because I'm a theoretical and mathematical physicist. So I try to use the math. I know some of the math that my colleagues don't know. Maybe they know other things that I don't know. And I can use that to answer some questions that are difficult if you don't know this kind of mathematics. And the mathematics that we use and to some extent develop further in general relativity is a part of differential geometry. Of course, general relativity itself is formulated in terms of differential geometry. So we developed some of this machinery further. There's an analysis aspect of this called geometric analysis that comes into play in some places. The relation between quantum information theory and quantum field theory is described, what we use in this approach, a very, very powerful machine of operator algebras. In fact, von Neumann algebras invented by von Neumann, who also invented, in some sense, the mathematical formalism of quantum theory in the first place. And finally, in quantum field theory, we use many things, but one thing that is very handy is microlocal analysis, which is a kind of version of the geometric optics approximation, which gives very strong estimates on wave propagations and on really things you need to know if you want to renormalize, so Popper says, quantum field theory. With this, I would like to thank you, and I hope you got some, at least very vague, impression what I'm doing scientifically here at Leipzig University and the Max Planck Institute.